Good morning. I will wait for a few more minutes and I will I'll start.
You got it, sir. And what will be our syllabus for Cat 2?
Syllabus that I will let you know by this probably up to magnetostatics, the first part of the magnetostatics. So far we have completed with electrostatics totally completed. So magnetostatics today about to start. First part it involves Bayer-Savart's law. So based on Bayer-Savart's law, calculation of magnetic field due to some current sources.
So could you please upload the previous slide?
Sorry, I forgot. After this class, I will upload the Cat 1, whatever is required for Cat 1, I will upload immediately after this class. Thank you for reminding.
Okay.
The screen is visible?
Yes.
Please confirm whether the screen is visible. Okay, very good morning, guys. We are moving to the second part of the subject, magnetostatics. So electrostatics, there is like you may feel like we have discussed so many things. The reason is we have discussed, we have revised the vector calculus. That's why seems like we spent a lot of time in electrostatics. And even with for capacitance, we spent some couple of hours. But the second part, that is magnetostatics, or the study of static magnetic field, it won't take much time. Then immediately we can move to the electrodynamics or electromagnetic wave. That too will not take much time. So rest of the subject we can say almost 60% we have done. So for rest is 40%. But in terms of mark distribution, that is different. Equal distribution will be given. But in terms of time required, maybe 40 to 45 or maybe 40% time. Not even 40, less than around 40. So moving to the second part of the subject, that is magnetostatics. Earlier we discussed about electrostatics, which is produced by the charge at rest. Charges are stationary. In this case, we are considering the charges are moving. If the charges are moving, we call it as a current or current flow. But the charges are moving with constant velocity, then we will call it as a DC current. So if some charges are moving with constant velocity, it will produce a magnetic field. But the produced magnetic field will be static. The moment the current flow happened through the wire, DC current flowing through the wire, you would notice a change in the magnetic field, but that will be constant, that will be static. It will not change with respect to time because the current flowing through the wire is not alternating. So produced magnetic field will be also static. So this part of that is, you can say this is considered this is second part of the module, second part of the subject, that is we will study or focus with the static magnetic field, the study of field produced by the charges which is moving with the constant velocity, or we can technically call it as a DC current. It can flow through free space or it can flow through vacuum or it can flow through conductor. But we are not going to much into this vacuum current flow. We will consider only the current flowing through the conductor, and we will see the fields produced. To calculate the field, as usual, the procedures are same. We will follow the same template. only the governing equations will be different. So early we used Coulomb's law or Gauss law. Here we will use Biot-Savart's law and amperes, which are we are already little familiar with. And the same this second part of the subject. So most of the discussion except the boundary condition will be merely a repetition of your school topics. But you would see a difference. You can see a major difference in terms of approach. The hope that you have recognized in the first part of the subject, you are not into much complicated derivation or problem solving. Similar problems you have solved already in the school level, but here the problem solving is quite easy because you understood the problem using the vector space, using the vector calculus, and you are fitting the problem with the proper coordinate system. So we are reducing the mathematics. We are reducing the time invested on the mathematics. Rather, we are investing more time on the analyzing the or understanding the problem with the help of vector. So magnetostatics, like electrostatics, you have quantities like electric field intensity, electric flux density. In magnetostatics, you have quantities like magnetic field intensity, the unit is amperes per meter, which is analogous to the current. B vector, it's for magnetic flux density. The unit is Weber per square meter. It's like flux density, right? So it should be per area, or you can use the unit Tesla. And these two related by this equation, B equal to mu h, where mu is the permeability, magnetic permeability. The unit is Henry per meter. Mu equal to mu naught into mu r. Mu naught is 4 pi 10 power minus 7. Sorry. Yeah, it's 4 pi into 10. Can anyone recall this? I think I don't know whether I'm writing correct or not. 4 pi 10 power minus 7, right? What is the value? I hope this is correct. Okay. If it is wrong, we can update it later. Moving to the magnetostatics, you need to recall few things. The difference between electrostatics and magnetostatics is the source. In terms of the source, if you consider in electrostatics, you have sources like point charge, line charge, defined using the or characterized defined with line charge density, surface charge, or volume charge. So here in magnetostatics, so the difference is in magnetostatics, like already we have discussed, right? The line current, surface current, and sorry, it is yes, and volume current. These are the three sources, like current flowing through the wire, current flowing through the sheet, and current flowing through the surface area. So these are the three sources in magnetostatics. Line current is called as line current density, surface current density, and volume current density. So only the governing equations will be different, and the sources anyhow, you can see it is like a static sources, stationary sources, but here the sources is not stationary. But anyhow, we are representing with, we are not going to take this term like dq by dt. Instead, we will write it replace it with current I. So the problem will be quite easy. But only difference is the direction. See, in electrostatics, the sources does not involve any direction, but here you can notice the direction is involved because current is flowing means you need to specify in which direction the current is flowing, either this direction or in the opposite direction. So current need to be specified. So source, while specifying the source, you need to specify the direction of the source or the current flow. So this is very basic rule that you need to recall. When current is flowing through a conductor, magnetic field will be produced, and that will be in circular loop that will be perpendicular to the wire. So this is the current carrying wire. Let us say I is the current, and if you consider a small elemental length, this will be dl. And see, if you're writing I alone, you can't specify the direction of current flow. That's why we used to write it together, and we call it as elemental current IDL, because I will let you know the magnitude of the current, and DL help us to identify the direction of current flow. So in this case, let us say it's if it is z direction, you can write it like IDL equal to I into dz. Now, if the current is flowing to establish or to find the direction of magnetic field, you can use the right hand. Uh, use your right hand to hold, or I can show it in picture, it will be easy for you. So to find the direction of resulting magnetic field, you have to use this rule. So with this, you can, without even see, with mathematically also you can find, but without mathematics, you can find the direction of magnetic field, resulting magnetic field. See, ultimately, this chapter purpose is you need to calculate the magnetic field due to current sources. So resulting magnetic field will be some scalar or some magnitude and some vector. So this is also very important. This is also important. Anyhow, we can visually by inspecting this given problem, you can able to calculate or predict this part of the problem. Sorry, this part of the solution. Without mathematics, it's possible. So you can get some 2 marks easily. You can get, or you can cross check your final answer. So to find the resulting direction of magnetic field, hold the wire, current carrying wire using your right hand. Current is, assume this in this case, current is flowing in this upward direction, and your thumb finger should indicate the direction of current flow. Thumb should indicate the direction of current flow. So the remaining 4 curl fingers will represent the direction of magnetic field. Hope you have got this point. Now let us say the current is flowing in this direction. Then what will be the direction of current flow? It will be circular loop, and that loop will be perpendicular to the current carrying wire. Let us say I dl is the current flowing, or I into minus dz, or sorry, minus I into dz, because it's in the z minus is the direction, right? So what's the direction of current flow? Use your right hand, hold using your right hand. So the thumb finger should indicate, should be point in the downward direction. Okay, then your 4 curl fingers will indicate this direction. This will be the direction of magnetic field. So this will be the direction of magnetic field. So you can use the right hand to easily predict the direction of magnetic field. Suppose, consider this wire is aligned in this axis. So what will be the direction of magnetic field? So thumb should indicate the right direction. So remaining 4 fingers will indicate, so this direction, right? This is the direction of current flow. Now, so now I think this picture is clear, but this picture is not quite clear, right? Because drawing, you need to draw a 3D picture, okay? 3D kind of picture, because wire and this loop should be perpendicular to the wire, right? So it's difficult to draw. That's why to avoid such confusion, what we can do is we can take a cross section. The same picture I can draw like let's say this is a current carrying wire. I want to know the magnetic field at this point. Point P1 and P2, 2 points I'm interested to calculate the magnetic field. So at this point, what is the direction of my magnetic field? Say P1. So the magnetic field lines are perpendicular to your screen, right? It is perpendicular to the screen. If it is perpendicular to the screen, then you can use this dot with circle. In this case, sorry guys, let us assume this is the direction of current flow. Okay. So the magnetic field lines are perpendicular to the screen, right? So if it is perpendicular, so in the cross section, you can represent the perpendicular direction by this shortcut representation. Okay, or sorry, it's not perpendicular. If it is outward, inward, these are the 2 possible directions, right? If it is outward, use the dot and circle. If it is inward, use cross and circle. Okay, so at point P, magnetic field lines are coming toward you, or it is perpendicular to the screen, or leaving from the screen. So it can be represented with this notation. At this point P2, magnetic field lines are getting inside or going inside. So if it is inside, inward means you can use this symbol. Okay, so you can write magnetic field at point 2 is this, and magnetic field at point 1 is like this. So it's very easy for us, right? It's very easy. Now, can you,
This is inward.
pardon?
Inward P2, sir.
Oh, sorry. Sorry, that's deleted. Maybe I will show with other picture. You can ask the question. For inward, cross and circle. Outward, dot and circle. So in this picture, this will be the direction of magnetic field. Let us say point P and point P1 and P2 where we want to represent the magnetic field. So how will you represent? At point P, it is inward or outward? It is inward, right? At point P1. At point P2,
Outward.
sorry. It's outward, right? It's outward. So it is sorry. Is this clear? Not only for magnetic field, even to represent the current flow also you can use the same convention. Okay, let us say there is a sheet and current is perpendicular to the sheet. It is flowing in this direction. Now if you see from the top view of the sheet, the current is it's flowing like in this case what symbol you will use, inward or outward? So this is the perspective view. So this is a top view. So you want to represent the current flow. So at the middle of the sheet, the current is flowing, right? Or you are seeing the current element. So the current is outward. Outward means you have to use this symbol, okay? So you can put I here. Or I is perpendicularly leaving, or it is leaving normal to the sheet, outward normal. You can say outward normal. Is any question?
No, sir.
Okay. So with this, we can. It's easy for us to start and even finish. So Boyard-Savart's law. That's equation is more than sufficient to understand all the problem or to calculate magnetic field due to any configuration of wire. Now let us take the same wire uh, which is carrying a current I. We want to calculate magnetic field produced by this current element. So it's not sufficient to represent the current carrying element with I. You need to represent with L or DL, IDL. So IDL is the elemental. It's called as current element. Hope you recall IDL equal to identical to KDS, that's identical to ZdV. So here we consider a line current, and we know that okay, let me directly write the equation. So the magnetic field produced, first point to observe is the magnetic field produced by the current element will be circular loop. So H will be always in the phi direction, right? Because it's circular loop, it will not be in the radial direction or it will not be in the theta direction. It is a closed loop, so you need to use phi. Either with the cylindrical coordinate system or spherical coordinate system, you need to go with phi. So most probably with the cylindrical coordinate system, you can finish all the problems in magnetostatics using the cylindrical coordinate system. So magnetic field will form a loop. Now the question is, what will be the magnetic field produced by this loop? Sorry, the current carrying element. Now, let us say this is the source. This is observation point P1. Point P1. At point P1, the magnetic field will be maximum. Okay, so this is the source. Now let us connect the source and the observation point. Let us say this is the observation point, right? P1 is the observation point. So the vector what you are drawing, we used to represent with R vector, right? R vector is the vector connecting source and the field point. P1 is the field point. Okay, so this is P1. Now if you consider a point P2, P2, which is along the axis of the wire, what will be the magnetic field? So we know already that the magnetic field will be always perpendicular to the wire. So along the wire, the magnetic field will be 0. Or if you take the point P3 here, what will be the magnetic field? Consider only this current element. Don't consider the current flowing the rest or rest of the wire. You consider only the current flowing through the wire. So magnetic field will be maximum at the this angle. Let us take theta equal to 90 degree. At theta equal to 90 degree, the magnetic field will be maximum. Okay, you can say H equal to maximum. At theta equal to 0 degree, magnetic field is minimum 0. What about magnetic field at point P3? It will not be neither 0 nor maximum, right? It is in between, right? Let us say theta equal to 45 degree. Then magnetic field will be, how much will be the magnetic field? So maximum by square root 2, right? So this way variation will be happen. So that's why we want to, this, you can see this is a sinusoidal sign variation, right? A sine or cosine variation. So this theta equal to 0, this theta equal to 90. So as theta equal to 90, we are getting maximum magnetic field, and we are getting 0, sorry, at 0 degree, we are getting minimum or 0 magnetic field. That's why we prefer to multiply these two. That is the source. This is the source. And what about R vector? R vector is a field. This is a field or observation point. If you do the cross product, why we are doing cross product? Because we want sign. That's why we are doing cross product. Then you will get the resulting magnetic field. Sorry, integration. You need to integrate. You need to integrate along the closed. See, actually, it's a closed or open. That the question really matters. But don't bother. Let us assume this is a open wire. If you take a closed wire, we should not take a closed wire. The reason is you need to include some source, right? There should be some source. Okay, so now let us not into the confusion like whether open or closed. Usually in this case it is a open wire. Okay, so if it is theoretically, if you assume this is a closed wire or closed loop which is carrying current, okay, then you need to take the closed line integral. Okay, so maybe as a generalized equation we can take closed line integral now. Now let me rewrite this equation, or the equation is available here. H vector is I dl vector cross r vector over 4 pi r cube. So if it is a open wire, you can use open, or if it is closed wire, that is theoretically only possible, you can take closed line integral. I dl vector cross r vector over 4 pi r cube. This is for the line current. If it is surface current, you can replace this IDL with K ds. Or you can write it in better way like K vector cross R vector into ds over 4 pi r cube. This is for surface current. Same way for the volume current, J dV cross R vector over 4 pi r cube. This is for the volume current density. So you need to recall only this equation. This is more than sufficient for the entire problem solving based on the Biot-Savart's law. Now let us calculate. It's going to be take really maximum 3 minutes time to complete this problem. Now let us calculate magnetic field due to straight filamentary conductor. In this, I don't want to draw, so that's why I'm using the picture available in the textbook. So this blue segment, what you are seeing is a wire which is carrying the current. It's a finite in length, so it starts from A and it end at B. Please notice all these things. So this is a source. Let us say this is the observation point. Why we are using cross symbol? Hope you understand. As the current is flowing upward, so if you observe from this point, it will be inward. The magnetic field will flow through the observer. Okay, let us say you are standing from here. Okay, so the magnetic field line will pass through you. Okay, pass inward. right? That's why this cross symbol we are using. So it's depending on, it's related to where you are observing. If you are observing from the other side, it will be different. While solving the problem, you need to be very careful about it. Okay. So what's the next step? You need to connect the source and observation point. Sorry, source and observation point. So this is the source, this is the observation point. Connect the source and observation point, you would get R vector. So once you got R vector, you can calculate R, then put all this into the equation, then you can solve the problem. Now, for this case, you need this formula. That is, as this is a wire, straight wire, you can use this formula, line current, magnetic field due to line current. You can use this formula. Now we need to find R vector and R cube. So before that, understand this problem can be solved using the cylindrical coordinate system. Rho phi z. The distance between the wire and observer is rho. Rho is the radial distance between the observer and the wire. And so A to B is the length of the wire. As usual, we will not consider the entire length. We will take a small elemental length. That length is dl. And we will calculate magnetic field at the observation point. Then finally, we will integrate from A to B. Finally, we will do the integration from A to B. That's what we will do. So initially consider the elemental length. What is the magnetic field produced by the elemental length? dl. Then finally, you can sum up. Or you can continuously add from A to B. That's what the approach is. And one more important point, how we are defining the length. If it is rectangular coordinate system, we no way you need to specify the wire length as z equal to 0, z equal to 2, z equal to 2 to 4, or z equal to 2 to 8, like that you need to specify. But instead of that, if you express it in angles, it is very easy easy because that your equation will contain sine and cosine. You can even your equation will be very compact form. Hope you recall the similar topic in electrostatics where to calculate the electric field due to line charges, we represent the length of the wire or the charge using angle. So there we got a sine or cosine in the equation. It is very easy to understand, right? Or it's very easy to solve the, or we can say we got very simple form of equation that's possible. Okay, that's why this alpha 1, alpha 2 were used. Now let us start. So now first what you need to find? I is dl vector. What is dl vector in this problem? Relative to this problem, what is dl vector? Come on guys, you should speak. What is dl vector in this problem? You can't keep dl as dl. You need to express it in terms of the cylindrical coordinate system. So in which direction the charge displacement happen, or in which direction the current flow happen? So current flow is represented, direction of current flow is represented with dl vector. Now in this case, what is the direction of current flow? Which direction current flow happen? Louder, please.
DZ.
Sorry, still voice is low.
So DZ.
Exactly, that's correct. dz. dl vector equal to dz. So it is not increasing along the radial direction or phi direction. The current is increasing or flowing through the z direction. So dl vector should be replaced with dz. Right? So dz. What about r vector? R vector is a vector connecting the source. This is the source. This point is the source. Source, and this is the field point, right? Field point. So from so that is R vector. How will you find R vector? So this is R vector. Now express or try to have the tangential and normal component, or write R vector in terms of tangential and normal component. So find the complete this triangle. What is this? This is rho. This is z. See, this is z. So at this point we have the source. Understand? At this point source is present, and this point observer is present. So it is rho into a rho. Hope you understand why I am taking this, because radial direction always will be in the positive, right? So it will be in the outward direction. Z, this is in the positive Z axis, so it's Z into AZ. Z into AZ. Now write the equation. From this, by using the Hertel rule, you will write like Z into AZ plus R vector is equal to rho into A rho. Therefore, R vector equal to rho into A rho minus Z into AZ. So you got equation for R vector. So numerator we have found dl vector, then r vector. What is dl vector cross r vector? That you need to find. So this is the one additional step. In addition, like if you compare with the electrostatics, as the source is not as a vector, there is no cross product. But in the magnetostatics, in the formula will contain a cross. You need to perform a cross product step. So what dl vector is dz, or you can say d is, sorry, you should not like dz into az. Okay, so dz into az cross product with r vector, rho into a rho minus z into az. Really, this is a powerful step. This particular step I am talking about. So what is the first step? Can you give me the answer? Just can you speak now? Rho into dz. What is az cross a rho? So cross product, you need to go in the cyclic order. So AZ cross A rho, AZ cross A rho, AZ cross A rho is A5. Correct? AZ cross A rho is A5.
Yes, sir.
Then what about the second term? Minus Z into DZ, AZ cross AZ. What is AZ cross AZ? If you find the cross product of the parallel vector, it will be 0, right? Because the angle is 0. So it is 0, right? So dl vector cross r vector is rho into dz into a5. So the numerator is ready. The denominator, that only that we need to find. Anyhow, we can take r vector. If you take the magnitude, you would get you will get a square root of r square plus z square. But still, we want to express it in terms of this z, and we don't want to keep z. We want to replace z with angle alpha. Is it clear until this step? See, what we did so far is we found the r vector equation, then dl vector, and we found the cross product. Maybe it need half a minute to complete this. Next step is you can, before plugging all this into this integration, now let us write r vector. R vector is rho into a rho minus z into az. If you take the magnitude, I'm talking about the denominator. If you take the denominator, it would be square root of rho square plus z square, right? That will be the denominator. But already we planned, like we don't want to express the length of the wire in terms of z. We want to express in terms of angle. Okay, so that's why what we will do is, this is z, this is rho, this is r. Right? So this is alpha, right? This is alpha, this is 90 degree. So rho over z is cos, oh sorry, you want alpha, right? You want find r, right? So we can't use r. Sorry, you don't use sorry, rho by z is tan, but we can't use this. We want r because I'm talking about only r denominator. So what you can use is either sine or cosine you can go with. Okay, so now let us write the formula for sine. Rho over r is sine alpha, or you can say r equal to rho over sine alpha. So rho into cosecant alpha. The reason for why I am taking sin alpha instead of cos alpha, if you take cos alpha, what will happen? Cos alpha is z over r. Again, that z term comes. We want to avoid z. We want to avoid z. That's why we are taking this. See, there are three possible equations you can take. You can use sine, cos, tan. You can use anything, but anyhow you can't use tan because we want to write the denominator r. So either you can go with sine or cos, cosine equation, on which we are prefer to write the sine equation. Is it clear? Now let us plug everything into the integration. So I is a constant, move it outside. So dl vector cross r vector is rho into dz into a phi over 4 pi. What's r we found early in the previous step? R was rho r equal to rho cosecant alpha, right? So it will be rho cube cosecant cube alpha. That's the denominator, right? But still there is an unwanted z term is there in the numerator. That dz you need to replace. That we don't want. Okay. So again, guys, hope you understand what we are doing now. That dz you need to rewrite in terms of alpha or angle. Okay. Again, get the help from the triangle, right angle. So this is alpha. This is what is this? This is r. This is rho. This is z. Now we want to replace z. Okay. So maybe you can use cos or tan. You can go, right, because it involves z. Now let me use this tan alpha. So tan alpha is rho over z. I can say z equal to rho into rho by tan alpha. So 1 over tan alpha will be cot alpha. So z equal to rho cot alpha. See, when in this case we want to rewrite z in terms of alpha. So if you want to write z in terms of alpha, either you can go with cos alpha or tan alpha. If you go with cos alpha, again the r term will come. We want to avoid that. That's why we go with tan alpha. See, there are n possible ways. Like we want to simplify the equation. That is why we are doing all this. Because later you should not think why we are taking cos instead of tan. Sorry, why we are taking tan instead of cos. You should not think. So z is rho cot alpha. We want dz. So dz is rho. Differentiation of cot alpha is cosecant square alpha into d alpha. That is minus cosecant square alpha. Differentiation of cot alpha is minus cosecant square alpha. Now you can replace the numerator, the dz, with let me take the I outside. So rho into rho cosecant square alpha into d alpha over that 4 pi is a constant term. The rho cube. Okay. So if you simplify this, you will get there is no space. So, okay, if you simplify, what you will get? Minus I over 4 pi integral. What is integral limit? Now we fix the integral limit. Integral limit, that is wire length is from alpha 1 and to alpha 2. Okay, so alpha is the angle like it's any point in the line. So the lower limit we represent with alpha 1 and upper limit we are representing with alpha 2. So integral limit is from alpha 1 to alpha 2. So this rho term is there. Here is a rho into rho will be rho square. Denominator there is a rho cube. So it will be 1 over rho. Rho will be also constant. So what numerator cosecant square, denominator it is cosecant cube. So it will be 1 over cosecant. So d alpha over cosecant alpha. That's all. Let me continue with the first page. I'm writing it again. So H vector is minus I over 4 pi rho 1 over cosecant. Cosecant is 1 over cosecant. You can write it like a sine alpha into d alpha. Integral limit from alpha 1 and to alpha 1 to alpha 2. So integral sine theta is, what is integral
Minus
sine
cos.
theta? Minus cos theta. Always there is a confusion. Let's go minus cos, right? So minus, already there is the minus here. So be plus. So 4 pi rho alpha, sorry, alpha 1 to alpha 2. So magnetic field due to finite line current carrying element would be I over 4 pi rho into cos alpha 2 minus cos alpha 1. This is a magnetic field due to, this is a such a compact equation. Strategically we wrote everything in terms of alpha, and now we can see, or let me explain the equation in the printed form. So this is a magnetic field due to a finite length of current carrying element. Now let us try to understand. As expected, magnetic field intensity is directly proportional to the strength of the current, and as you are moving away from the conductor, the strength of the magnetic field will reduce, and it's a function of the length. It's a function of length. So these are all scalar parts. What about the vector part? What is the direction of magnetic field? It is along the phi direction. What is phi direction? See, this is the direction of current flow. Hold with your right hand. Hold with your right hand, and this is the direction of magnetic field. So magnetic field is inward, right? So inward, why then representing with a phi direction? Because magnetic field will be always in phi direction, right? It will be in the phi direction. So what is this direction? This is a phi direction, right? This is positive a phi direction. So with respect to the observer, it is in the positive a phi direction. Now please try to answer this. So in the previous slide, we assume observer is at point P1. Okay, so this will be the direction of magnetic field, and maybe in the paper we can represent it with this symbol, right? It is going inward, so you can represent with this symbol. So magnetic field at this point can be represented with this symbol. And same way here, it is perpendicular to this screen. Okay, so you can use this symbol H. Okay, H vector. It is outward, right? It is outward. Now, if you write it as a vector, you can say like H along a phi direction. It is in the, with respect to this observer, it is in the positive a phi direction. It is in the positive a phi direction, right? If you take this point, what will be the direction? Let us say this is H1 vector. Let us say this is H2 vector. That's observation point 2. What is the direction?
Minus
Minus minus a
H.
phi.
A5.
Minus a phi. Right? So this is in the opposite direction because you are in the other direction, right? So it is in the opposite direction. Okay, so you should use the minus a phi. So it is related to where you are observing. Okay, it's related to where you are observing. No, would it be minus a phi or plus a phi?
Oh, plus. Sir.
Pardon?
I think minus.
Better you can check with this diagram. See where that minus sign came. See everything I told earlier, a critical step, this is a critical step, right? So dl vector cross r vector, that is a source, this is a field. If you take the cross product, this will give you the resulting direction of magnetic field, right? So either the observer is here or on the other side, maybe on this side. If you take other side, what will be the direction of r vector? This will be the direction of r vector. This might be the direction of r vector. How will you write the equation? Still, in that case also, the direction of magnetic field is dz into az, right? Cross product with r vector. Okay, what will be the r vector equation? In that case, what will be the R vector equation? Please try with your pen and paper and tell me. Because for further problem solving, it is totally relying on the two important points. Like one is calculating how you are calculating the angle correctly, and other is how you are understanding the observer, how you are recognizing the location of the observer. Now the question is, if the observer is on the other side, what will be the R vector equation? Will it be different or same? Come on. See, what I am asking is, in this case, we observed observer is here, right? P1. Now I'm asking you to keep the observer at point P2. What will be the change in the answer? That's what I'm asking. Come on, guys, you should speak. You should think and speak. So in this case, dl vector cross r, dl cross r vector. Dl is dz, right? Dz into az. Now tell me what will be the, in this case for point P2, what will be the dl vector? Let us solve one after other. What is dl vector for this point P2? For point P2 also it is along the z, right? The current is flowing the same direction. So dz into az. Now the question is r vector. So this will be the r vector, right? The r vector. And this is rho. So if you take this point, this will be r vector, and this will be rho. This will be z into az. Now tell me whether r vector will be different or same in both cases, point P2 and P1.
I think in the end it's the same.
Yeah, it will be same. Yeah, it will be same. You're correct. It should be same, right? It will be same. So in this case and the other case, it is same. DL vector cross R vector is same. It's a symmetry, right? It is like rotating. Whether you are at point P1 is here at a 90 degree, phi equal to 90 or phi equal to 0, and not matters. It will be same. Okay, so the answer will be, if you take the cross product, what is the answer here? Like DL vector cross R vector, if you take it is along something along the phi direction. Same way it should be also along the phi direction. Okay, now the point is, don't think like, see, now I will redraw the picture. Now question is, if the observer is here at point P1 and P2, that was the question I have asked you, right? So this is the direction of magnetic field. Now at point P1, what is the magnetic field? H vector equal to H along A phi direction. Now answer this question. Now what will be the magnetic field at point P2? H vector is H along plus A phi or minus A phi? I think early the answer was minus A phi. Now tell me whether it is minus, still it is minus A phi or it is plus A phi?
Plus.
Yeah, it should be plus A phi only. Okay, so if you take the cylindrical, guys understand, if you take the cylindrical coordinate system, this represents the direction, like this direction represents the plus A phi direction, right? So either you are at point P1 or P2, that doesn't matter. Okay, or assume you are standing here, other case you are standing here. Okay, so in this case, plus A phi means it will inward. Okay, it will pass through you. In the other case at point P2, plus a phi means it will outward, it will pass through and it will perpendicular, or you can say it is perpendicular to the screen, right? It's outward to the screen. It is going inside the screen. Point P1, it is going inside the screen. Point P2, it is leaving from the screen. Okay, so in terms of cylindrical coordinate system, both cases it will be a phi. Okay, now see guys, any questions? If anybody not able to understand this, or do you think it is not correct? Now other case. Now let us assume Cartesian coordinate system. Let us assume this is a Cartesian coordinate. So let us say this is x, this is minus x. Okay. Now, what will be the magnetic field for this case? Case 1. What will be the magnetic field? Magnetic field is along which direction? If you take the Cartesian coordinate system, forget about the cylindrical, consider the Cartesian coordinate system, and for to express the magnetic field which is in this direction, what will which direction you will use? Please try. These guys, even if your answer is wrong, it's okay. See, it is like there is a wire. Wait, I will use some different color. What is the time? Oh, that's why you guys are not speaking. It is
50.
so within a minute I will try to complete. So this is the wire, right? So this is the direction of magnetic field. Now the observer is here at this point P, right? Which direction magnetic field is going? Magnetic field is going in this direction, right? In this direction. What is this direction? Now at least you tell me now. What is this
Inwards.
direction? Pardon?
From inwards to outwards.
Inverse to?
Like it goes inwards in Y.
No, 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 not Y. This direction, it is going this direction, right?
Minus x.
Yes, yes, yes,
Minus
yes.
x, yeah, correct. Minus. I think this picture is not clear. Okay, plus x. So it is minus x direction. Same way, if you consider this point, what is the direction of magnetic field? It is in
The
the plus
opposite.
x direction. So it will be h vector is h into a x. If you can able to understand this, no one can stop you in getting 10 mark. This is the only point you need to understand. And this magnetostatic, all the problems related to magnetostatics, because it involves a current which is flowing in certain direction. You need to calculate the correct direction of resulting magnetic field. Some cases in most of the cases you can use your right hand rule, but the problem is you need to clearly recognize for the given coordinate system what is the direction of magnetic field. It's AFI or minus AFI, all this. Okay. Okay. Anyhow, next class we will solve some 2 examples. We will see. We will apply the same approach. We will apply the same approach. Within fraction, you can able to tell. Okay. And one
So
more
at
thing.
no point negative is possible, right?
Pardon?
At no point negative is possible, right?
Sorry, it's Delhi and
Negative sign doesn't come at all, right?
negative sign. Yeah, no. In this case, negative sign, right? This point it is h into minus x, right?
Oh, yes.
Okay, it's possible, yeah. So it's a matter of assume, like usually for discussion what I suggest is you assume like you are standing here, okay, standing here, and what will be the direction of magnetic field. If you think like if you realize a problem using such pictures, then it's very easy to tell the answer. Okay, anyway, it's time's already, it's late. So next class we will say take some 2 problems, and we will have some better understanding. Thanks for joining. You may leave now if there is no questions. If you have some questions related to this, please stay, or you can speak now.